Okay, so the Jyotsna has asked me to give some informal lectures on analytic number theory by way of introduction for self-study. Now, I've written this book, Problems in Analytic Number Theory, so that students such as yourselves could study on your own. And I would recommend that you do that. I think you can probably, there are some creative methods of getting hold of the book, which I will not spell out because this is being videotaped. Now, let's see, what can we say? Firstly, let me say a few words about analytic number theory. Generally, analytic number theory is to use analysis to study problems in number theory. So uses analysis to study questions in number theory. Now, what kind of analysis? It can be real analysis, it can be complex analysis, or it could be p-adic analysis. So it could be any one of these types of analysis. P-adic is a recent entry into the methodology in analytic number theory, and I have a book on p-adic analytic number theory, but if you're interested in studying that, you can do that independently of both these things. But in this kind of informal talk, we will focus only on real and later on perhaps complex analysis. Okay. Now, generally speaking, we will look at methods rather than theorems. So we'll pay attention to methods rather than results. Okay, so this is just a definition of, working definition of what analytic number theory is. Now, the focus of study in number theory are arithmetical functions. Arithmetical functions are, by definition, functions, complex valued functions defined on the natural numbers. Those are arithmetical functions. And generally speaking, we would be interested in a variety of questions. Growth of these functions, growth of f at n as n varies. Sometimes we may be interested in finding out the behavior of these partial sums and try and understand these sums, asymptotics for such functions. And so that's basically the focus of study. In the class of arithmetical functions, of course, there are several types of functions. The most common, perhaps, that we will be looking at are multiplicative functions. And these functions are, if they have the property that f of mn equals f of m times f of n, whenever m and n are relatively prime, we say the function is multiplicative. Okay? We say the function is completely multiplicative if f of m n is equal to f of n times f of m for all mn, whether they are coprime or not. It doesn't matter. So those things are completely multiplicative functions. We say a function is an additive function if we say if f of mn is equal to f of m plus f of n whenever m and n are relatively prime. And we say something is completely additive if we remove that restriction. F of mn is f of m plus f of n for all mn. Okay, so these are several categories of functions. Let's have a look at some examples. Is there an eraser here or? Okay. Oh, there is? Here? Is there an eraser here? Let's see. Oh yeah, there is. Okay, thank you. Yeah. Okay. Thank you. Yeah. All right. Let's look at some examples. The divisor function. So d of n is the number of divisors of n. Okay. So for example, d of 2 is 1 and 2, two divisors, right? D of 2 is 2. D of 3 is also 2. D of 5 is 2. D of 6, though, is 1, 2, 3, and 6, so 4, right? It's 4, etc. So this is the divisor function. So clearly, if I was given a number, now you know that every natural number can be written as a product of prime powers uniquely, unique factorization theorem, unique factorization. So you can see that any divisor delta of n will then have to look like p1 to the beta 1, pk to the beta k, right? With these beta i's less than alpha I, right? 0 less than beta I, less than alpha I. Any divisor looks like this. Conversely, if I pick any such number with this restriction, it'll be a divisor. So there's a one-to-one correspondence between divisors of n and all numbers of this type. Therefore, how many choices of beta I do I have? Say it loudly. Alpha I plus 1, exactly. So there are alpha I plus 1 choices for each of them. Therefore, we have an exact formula for d of n. Right? That's the number of divisors. So the question is this a multiplicative function, a completely multiplicative function, an additive function, or a completely additive function, or none of them? What kind of a function is it? Any guesses? It clearly depends only on the factorization, and if m and n are relatively prime, the divisors of m times n can be obtained by taking a divisor of m and a divisor of n and then clumping them together. They seem to be independent, right? Therefore, it's multiplicative. So this is a multiplicative function. D of n is a multiplicative function. Question is it a completely multiplicative function? Is it completely multiplicative? All you need to do is you have to come up with an example, correct? Okay. Well, let's look at d of 8. How many divisors does 8 have? That's 2 cubed, right? So 4. But this is not equal to d of 2 cubed, right? All you need to do is come up with an example to show that's not the case. So it's not completely right. Actually, we could have taken d of 4 also. d of 4 is what, 3, right? And it's not certainly okay. So it's not completely multiplicative. It's a multiplicative function, and so this is our first example of an arithmetical function. We may want to study several things. So so this is what number theorists do. Once you give me an arithmetical function, you try to study this function now from many, many different angles. And one of them is how fast does this grow? What is the growth rate of d of n? We'll kind of try and figure out how fast is it growing. Second is things like how does the sum d of n behave, n less than x? Do we have any asymptotic behavior of these partial sums of the divisor functions? That gives us some sort of also some other information on how the thing is growing as a function. And sometimes we can be more innovative and perhaps study what are called moments and take powers of the divisor function and try and study moments, so-called moments of the divisor function. This kind of stuff gets harder and harder. It sounds very easy to formulate, but it actually leads to some very interesting stuff. Very, very interesting stuff. And the story is not over yet, and I'll explain that in a second. So this is one good example of an arithmetical function. Oops. So what do you do when things like that happen? Do you just I guess you'll edit the film, right, for all these bloopers, what they're called, right? All right. Yeah, so this is one example of a divisor. So let me give you another example. the Euler phi function, which you probably so phi of n is the number of j's less than n which are relatively prime to n, correct? That's the Euler phi function. And the question is this a multiplicative function or not? And so is this multiplicative? Okay. So, well, you have to ask this question and answer this question by, you can answer this question easily by trying to first find a formula for phi of n. So here's a simple way of finding a formula for phi of n. So here I have all the numbers 1, 2, 3, dot, 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 up to n, okay? All the numbers. I'm going to determine the probability that a random element between 1 and n is co-prime to n. Okay, I'm going to do that. So how many elements are co-prime to n from 1 to n by my definition? Phi of n. So the probability that a random number j less than n is co-prime to n is the number of such numbers divided by n, right? It's phi of n over n. So that's the probability. On the other hand, what does it mean to say some number is co-prime to n? It means it's not divisible by any prime dividing n. Okay, what's the probability that a random number is divisible by a prime p? 1 over p, right? That's the probability. And you want it to be not divisible by p, so it's 1 minus 1 over p. And you want this to happen for every prime dividing n. You don't want it to. So each factor here represents the probability that a random number is not divisible by p, and you want this to happen for every prime dividing n, therefore the two probabilities must be the same. Okay, so this gives us a formula for phi of n very quickly, right? And we see that phi of any prime power, p is a prime. Okay, p is a prime. If I take phi of p to the j, I see immediately it's phi of p to the j divided by p to the j is equal to 1 minus 1 over p. So I immediately see it's p to the j, p minus 1. J minus 1, sorry, j minus 1. Thank you. Yeah. Right? P to the j minus 1, p minus 1. That's what you get. So now the question is this function a multiplicative function? Yeah, it's clear from here, right? It only depends on the prime factorization, and they're independent. So this is multiplicative. And I'll leave it to you to check that it's not completely multiplicative, okay? It is not completely multiplicative. That's easy to check because phi of p squared is p times p minus 1. It's not equal to phi of p, which is p minus 1 squared. So this is a multiplicative function, but not completely multiplicative. So we seem to be meeting a lot of nice multiplicative functions, but not completely multiplicative functions. All right. This is a very useful function to study. It appears all over the place in mathematics, not just number theory. And I'm sure that most of you know the famous Euler's theorem. If a and n are relatively prime, then a to the power 5n is always congruent to 1 mod n, right? I mean, you must have seen this theorem somewhere, sometime in life. and it's very useful to know that fact. Okay, let's take a third example. Let's count the number of prime factors of n. Prime divisors of n. Okay, number of prime divisors of n. So for example, omega of 6 is 2 because it's divisible by 2 primes. Omega of 12 is also 2 because it's only divisible by 2 primes, etc., etc. Omega of any prime power is just 1, p prime. So I think it's pretty clear that if m and n are relatively prime, the number of prime factors of mn is equal to the number of prime factors of m plus the number of prime factors of n, right? So this is an additive function. And the question is it completely additive? Answer? Is it completely additive? No. Why? Yeah, exactly. P times p squared. Omega of p squared is only 1, but omega of p plus omega of p is 2, right? Yeah. No. Okay, so it's an additive function, but not completely additive. And again, here, one would like to know study how the function omega of n behaves, n less than x, and see how it's growing. And more generally, we would like to take powers of the function and study what are called moments. These are all things called moments. So we'd like to study things like that, and this is an important chapter. The study of these things is an important chapter in what's called probabilistic number theory. So it's another offshoot of analytic number theory. Let me give an example of a completely additive function. What's called the Liouville function, omega of n, is the number of prime powers, prime divisors counted with multiplicity, or prime divisors counted with multiplicity. Well, what I mean here is if n is equal to p1 to the alpha 1, pk to the alpha k, then omega of n is going to be equal to alpha 1 plus alpha 2 plus alpha k. Okay, so that's the counted with multiplicity. I'm going to count. Before we only counted 1 plus 1 plus 1 for this omega of n, but now this capital omega of n will be, I'm counting it with multiplicity, so I plug the thing in, okay? So this is a completely multiplicative function, completely additive function, sorry. Completely additive, okay? So this is completely additive. It's clear because it's counting the multiplicity. Now it's okay, right? Completely additive. And again, one could ask questions about the behavior of this function and how does these sums and moments behave. And that takes you again into another chapter of probabilistic number theory. So I'm asking all these questions about the behavior of these things, and so it might be interesting to come up with some technique as to how to approach all such questions. But before I do that, I should give you one more example. Give you one more example. I guess it's number 5. This example is called the one mongold function. After the person who discovered it. Very useful notation, I suppose. This function is defined as follows. Lambda of n is equal to log p if n is a prime power, p to the alpha, p prime, and it's 0 otherwise. Okay, so this function is, in some sense, it detects prime powers. And every time it's a prime power, it'll only pick up the prime, though. It won't pick up the power. And here's the interesting thing about lambda of n. It is, firstly, is it a multiplicative function? No. Is it an additive function? No. Right. It's neither multiplicative nor additive. However, it's going to be an important function in number theory, so we'll look at it. So there are functions which are neither this nor that, which are nevertheless important, and we should study them too. Okay, now the interesting thing is we notice that every number can be written as a product of prime powers uniquely, unique factorization. So log of n is equal to alpha 1 log p1, alpha k log pk. So that's obvious, right? I just took logs. But now I can rewrite this very neatly as a summation over the divisors of n, lambda of d. Because this guy is going to be 0 unless d is a prime power. And whenever d is a prime power, it's going to spit out log p. But it'll spit out log p how many times? As many times as alpha 1 times. So this is the how it's. But writing log n in this fashion is like it's tantamount to like writing a function as a Fourier transform or something like that. So this is you're writing log n as summation d divides n of some function. So if you think in terms of some integration, this analogous to some integration and some function, this is some sort of transform of log n. And this point of view will be useful in general in trying to understand asymptotics of summatory functions, okay, as we'll see in a second. Are there any questions so far? I mean, it's pretty straightforward. So the whole chapter 1 is about arithmetic functions. So I gave you a very quick introduction to chapter 1, and you can study a little bit more in detail. At your own rate, at your own speed. Okay, so that's a summary of arithmetical functions. Let me say a few words about what are called summation techniques. And the most important technique is what's called the method of partial summation. Sometimes called Abel summation, after Abel, who discovered it. Okay, so this basically it says let a sub n be a sequence of numbers complex numbers, and f of t a differentiable function on for t bigger than or equal to a. T bigger than or equal to 0. Say. It doesn't. You can restrict and relax these conditions, but it's not terribly important. Set a of x to be the partial sums of a sub n. Then the sum n less than x a sub n f of n is equal to a of x f of x minus the integral from 1 to x a of t f prime of t dt. So this is the first tool I am putting into your hands for the purpose of studying in analytic number theory. So what is the tool? The tool is it's telling you how to change a sum into an integral. That's the amazing thing. And integration is very easy. You've got lots of methods, calculus and so on and so forth. So this is the first powerful tool that you have available. As long as you know something about the behavior of the partial sums, summation an, you can change a sum like this into an integral. And you will see in a second how powerful this idea is. In fact, it more or less animates all of analytic number theory. Let's try and prove this. Proof is not terribly hard. So notice that a sub n is a of capital N minus a of capital N minus 1, right? I mean, you sum a1 to an minus a1 to an minus 1. Okay, so it's clear. So what we do is we will take this sum and replace an by a of capital A of n minus capital A of n minus 1. This is Abel's proof. Okay, so, I mean, he didn't write it like this. I'll tell you his motivation later on, but this is his starting point. So he starts out like this: a of n minus a of n minus 1. Like so. Like that. And now you do what you think you do. You you just write it like this. Fair enough. Now what I'm going to do is I'm going to change variables here. And I'm going to so as n is running up to x, n minus 1 will run up to x minus 1. So I'll just change n minus 1 to n again. And this will be f of n plus 1. And then I'm moving only up to x minus 1. And now that I have that, I combine. This sum is going up to x, this sum is going up to x minus 1. So now there's a small issue about x being an integer or not. So let's just assume for a moment that x is a natural number. Okay? So maybe I should have said first suppose x is a natural number so that we don't need to worry about these small idiosyncrasies. Okay, so this sum is going up to x, and this sum is going up to x minus 1. The new term here is the x term. And then I can combine both of these sums going up to x minus 1. Like so. Okay? Then I write this as the integral from n to n plus 1 of f prime of t dt. Well, there's a, oh, sorry, here's a minus. So here, yeah, it's a minus. No, that's a plus. Okay, so this is a minus. Yeah, you're right. Yeah. So it's a minus. That's right. Okay? Now, making the observation that in the interval n to n plus 1, a of n is actually the same as a of t, for t, except at the endpoints. But you know, in a Riemann integral, if I fudge the endpoints, it doesn't really matter. So this whole thing then can be rewritten as a of x, f of x, minus the integral. Well, these integrals are going from n to n plus 1, and n is going up to 1 to x minus 1. So the whole thing is going up to 1 to x, and here I have a of t, f prime of t dt. Everybody okay with this proof? And now you can, I'll leave it as a small exercise for you to figure out that when x is not a natural number, this is still valid. You just have to do a small one more line of calculation. Okay? So this is still valid. Still valid if x is not a natural number. So you get this is the proof. So the proof of this changing a sum into an integral is a very, very important tool in analytic number theory. In fact, I would say it animates a good chunk of it. So having this in hand, we are now in a very good position to answer some of the questions I was asking about what is the behavior of those sum of arithmetical functions, things like that. So let's try and see what we can do with it. Is it okay? Now I'll rub out this proof here. So let's look at a few examples. Let's look at, for example, the following question: summation n less than x, 1 over n. What is the asymptotic behavior of this function? Let's look at that. Now, I want to apply this lemma, or this partial summation lemma, and this is what I'm saying, you know, in mathematics, not just number theory alone, mathematics in general, and probably in science as a whole, what you have to learn is you have to learn how to use the tools. And if you just know one tool and you really know how to use it, you can probably make a career out of it. Okay, so this is one tool. If you know how to use it, you can probably make a career. I'm no joking, you know. So that way, you look at this thing and you now try and figure out, I want to find the asymptotic behavior of that. I want to use this and change it into an integration. So this is telling you somehow, what am I going to pick for a sub n? What am I going to pick for f of n? Okay. Now if you pick a sub n to be 1 over n, you will need some information on part. That's exactly what I'm trying to do. So why would you pick that, right? So you should pick a sub n to be something you already know. So probably I should pick a sub n to be 1 and f of n to be 1 over n. So in trying to do this, pick a sub n to be 1 and f of t to be 1 over t in Abel's lemma. Okay? Then what happens? Summation n less than x, 1 over n, is, well, first thing, what is a of x? A of x is n less than x, 1. Right, in this case. So that's just the greatest integer function, right? Everybody knows about this greatest integer function, right? So this is a of x, which is the greatest integer of x, times f of x, which is 1 over x, minus the integral from 1 to x, a of x, a of t, which is greatest integer of t, times the derivative of 1 over t, which is minus 1 over t squared, right? So this becomes plus t squared dt. So this is an interesting theorem in itself. It tells me that summation, what I was interested in, all of a sudden got changed to integrals. Now, the greatest integer function x and the number x differ by at most 1. Okay? So it's a good time to introduce a notation also. So let me just do that. This is an important notation in mathematics, the big O notation. We say a function f of x is big O of g of x if there exists a constant kappa, okay, such that f of x is bounded by k times g of x. Usually g of x is positive anyway, okay, but we'll keep it like this for all x as x tends to infinity. For all x sufficiently large, or for all x. Good notation to have. It's a very nice notation. It might look like, well, you know, you don't need this notation, you can keep inequalities, but you know, sometimes actually all the time in mathematics, notation can be everything. For example, the idea of 0 as a symbol of nothing is a very profound notation. And that changed the world, right? Created the decimal system, changed the world. So notation, it can be everything. So here, I'm going to introduce this big O notation. And this notation is going to help in not worrying about inequalities. So that way, I'm going to write x, the greatest integer function x, as essentially, I'd like to think of it as pretty close to x, but the difference is it's bounded by 1. So big O of 1 means it's actually bounded, right? Big O of 1, that's the notation, okay? So x plus something bounded by 1. All right, so if I write that for this greatest integer x here, then that's x plus something O of 1. So now we can rewrite this as summation n less than x, 1 over n equals, well, the numerator is now x plus O of 1 divided by x, plus the integral is now 1 to x, t plus O of 1 divided by t squared dt. Fair enough? And now x is just 1 there, plus O of 1 divided by x is O of 1 over x. Okay? Nice notation. Plus integral t over t squared dt, that's just log t. So it's just log x. and then integral 1 to x O of 1 dt over t squared. Okay? And so this is something bounded. This is a convergent integral. So this whole thing is O of 1. Bounded. So in other words, I've shown that summation n less than or equal to x, 1 over n, is equal to, this is the main term, but everything else is bounded. Okay, so I can write that down. So this theorem is very nice because it gives me immediately, without any difficulty, asymptotic information without too much work. I just have to know how to use this Abel lemma. So thus, summation n less than x, 1 over n, is log x plus O of 1. Okay? Now, if you look at this proof, you can actually do better than this. Because you wasted a few things. So we go back and check what it is that we wasted. Now, I wrote my function greatest integer x as x plus O of 1. What I'm going to do now is I'm going to write this as x minus what's called the fractional part of x. So this is my notation. This is the definition, x minus greatest integer of x. Okay, so this is what's called the fractional part of x. So in this calculation, we, of course, were able to get the asymptotic behavior very quickly. However, if we take a little bit of care and shove this in here, so here now we will say x minus fractional part of x t minus fractional part of t, and then let's just do this calculation one more time. Then what happens? Well, the first one is 1. The second one is fractional part of x divided by x, but that's still plus O of 1 over x, so there was no problem there. In the previous, it matches the previous calculation. But this time, this is t over t squared, that's still in log x. But this time, I get 1 to x of fractional part of t divided by t squared dt as a term. And before, I just sloppily put O of 1 there and said this whole thing is bounded. But now you can see that this is actually a convergent integral. So I'm going to rewrite this. Well, I'm hoping you've memorized this now. So keep this here. So notice that, with a little bit more care, with some care, we see summation n less than x, 1 over n, is equal to, what is it? I can't see on the board. Okay, 1 plus O of 1 over x plus log x minus the integral 1 to x fractional part of t dt over t squared. Okay, and then I'm going to write this guy here as equal to the integral from 1 to infinity fractional part of t dt over t squared, and subtract what I added from x to infinity fractional part dt t squared. Okay. The advantage of doing that is this is a number now. It doesn't depend on x anymore. Okay, so this is some sort of constant, c, call it. And now this guy here is an integral which goes from x to infinity, but the numerator is bounded by 1. The denominator is t squared, therefore I can just bound it by the integral from x to infinity dt over t squared, which is 1 over x, right? So this is all 1 over x. Therefore, this compares with this error term here, and so the final result here is that you get log x plus 1 minus some constant plus O of 1 over x. Now you may ask me, well, I've got an O of 1 over x here, and I have an O of 1 over x here. Isn't it 2 times O of 1 over x? And the answer is, of course it is, but you don't care because this O means up to constant, so you don't have to do that. You don't have to put it twice. That's a convenient notation. Again, it's notation, okay? So this is better than before. This number here is often denoted gamma, and it's called Euler's constant. If you go back to your work. So what we have now is using Abel's summation method, we actually have a very interesting theorem that the behavior of this function is log x plus a constant plus something that goes to 0 very fast, which is a very good theorem. You'll see that it's very useful to have this particular theorem. Okay. This is first example. Let's do another example. Determine the asymptotic behavior of summation n less than x log m. Okay, so again, but for the Abel lemma, we want to try and see what to pick as what, an is what is f of n, so on and so forth. Well, again, we'll pick up a sub n to be 1 and f of t to be log t. Fair enough? Then apply Abel. Sometimes, in the literature, people just say by partial summation. That's what they're doing. They're applying this lemma, but then you have to figure out what was a sub n, what was the function, because they won't tell you. It should be, this is when you read that phrase in the literature, that's what you have to check. So now we know how to do these things. You just go log n. So a of x is greatest integer of x, log x, minus the integral 1 to x, greatest integer of t, times the derivative of log t, which is 1 over t, right? T. Okay. So this time we're going to do the same trick as we did before. Greatest integer of x is equal to x plus O of 1. Something bounded. So if I do that, what do I get? I get x plus O of 1 log x minus the integral 1 to x t plus O of 1 dt over t squared. Okay? So this time you're going to get x log x. Pardon me? Oh. What do I have? T. Oh, just t. Sorry, yeah. Not t squared, sorry. Correct, thank you. So x log x plus O of log x, right? Minus the integral of, well, t over t is just 1, and the integral of 1 is x minus 1, right? And then I have an integral big O of 1 dt by t, which is big O of log x. Okay? Now, keep in mind that, so what I have is here x log x minus x plus 1 plus O of log x plus another O of log x, but that's O of log x again. And log x is bigger than 1, and so this term is irrelevant now. See how this whole business works? There's no point keeping that silly 1 there, because that silly 1 is bounded by log x. I mean, it doesn't make any sense for you to have carried it anyway, so you have this plus O of log x. So you have a nice formula again here, which I will write here as summation n less than x log n is x log x minus x plus O of log x. And you may ask, hey, maybe you could do better like we did there. And the answer is yes, you can. And that's called the Euler-Maclaurin sum formula. You kind of keep on refining the thing a little bit more and more, and you can do better than that. But for the purpose of this initiation into analytic number theory, maybe this is good enough. Any questions so far on this stuff? Okay. Now these might look boring to you, but believe it or not, these are actually quite important results in number theory. And we have to credit the genius of Chebyshev, who recognized that these simple, silly results can give you information about the distribution of prime numbers. So let me say a few words about that now. Practically all of number theory is preoccupied with the distribution of prime numbers. Prime numbers, as you know, are the building blocks of all natural numbers. And just as physicists study the atomic structure of nature, because the atoms, protons, neutrons, and so on and so forth are the building blocks of all of nature, similarly, prime numbers are the building blocks of all of mathematics. So if we want to study mathematics, it makes perfectly good sense to be studying prime numbers, because they're the building blocks of all the numbers. And in order to understand prime numbers, we'd like to ask various questions about them. That's why number theory is preoccupied with that. So one of the first questions about prime numbers is how are they distributed? So let pi of x be the number of primes less than x. Now, I think most of you know that there are infinitely many primes. You know this usual Euclidean proof. If there were only finitely many, you multiply them all together, add 1, and then it can't be it has to be divisible by one of the primes that you started with, but it can't be, because it means it divides 1 and there's a contradiction, right? This is the proof that goes back to Euclid. Okay, in a second I'll give you another proof of that. And then you may ask me, why do you give another proof of that? Well, it's because, as I said at the beginning, it's not results per se that we're interested in methods. So if you give me a new proof of something else, that's very valuable, because that means you've stumbled on a new method. That's why these are important. Okay, so we now look at pi of x, the number of primes up to x. And I believe it was Gauss who first conjectured that pi of x is essentially asymptotic to x over log x. I mean, he made a more precise conjecture, but I don't want to talk about that now. But so this was the conjecture that Gauss made, apparently as a teenager. Okay, so this is what the story is. The question is whether or not we can prove this. So this is a conjecture of Gauss, and Chebyshev in the 1850s, I think, I might be wrong on the dates, but roughly around that time, showed that there exist constants A and B positive such that pi of x is less than bx over log x and is bigger than ax over log x. So at least it grows like that. Whether or not we can prove a of x is asymptotic to that is another question, but it grows like this. And he struggled very hard to prove this. He kept getting better and better numbers. These numbers, he started making them closer and closer to 1. And then he proved the remarkable theorem: if the limit exists, x over log x, if this limit exists, then the limit is 1. So he managed to show that the key idea or the key part of the problem is to show the existence of the limit. And all of these two results, both of these results, he proved using nothing more than Abel's lemma. Okay, so it's probably a good idea to show you that and maybe stop for today and then continue on Friday. So how does this work? How do you how do you do that? Well, the secret is here. The secret is here, apparently. So let's go back. Let's recall the von Mongold function. Let's recall that. Remember lambda d again? Lambda d spits out log p whenever d is a prime power and 0 otherwise, right? So we know that. So this is somehow not quite, but somehow like a characteristic function of prime powers, except it's weighting the prime with the log p. It's a weighted characteristic function. So on one hand, we know sum n less than x log n from this. So we know that. On the other hand, we know that log n is this. Therefore, we put that in here. This equals summation n less than x summation d divides n lambda d. Put it in there. And now we interchange summation. Natural thing to do in mathematics when we do two sums, right? If they're absolutely convergent, you can interchange. So d is dividing n and n is less than x, therefore d is less than x. And inside, I'm counting n less than x, d divides n, 1. Right? That is, how many numbers are there less than x which are divisible by d? Well, they have to look like d times t. And d times t has to be less than x. So t has to be less than x over d. Therefore, this number is nothing but the greatest integer of x over d. Right? Therefore, this is equal to summation d less than x, lambda d, x over d. So you have this very remarkable connection between the two now. Something, we're getting very close to some information about primes here, okay? Now, you'd like to do the obvious of removing the square brackets. Like to do that. And so actually at this point, Chebyshev got a bit stuck. He knew that this identity, on one hand you have this silly thing coming from just calculus, and on the other hand you have this connection to number theory, and somehow you should be able to get some information on primes from this identity. It's too good to be true. Therefore, you have to be able to get some more information from this thing. So the problem is, of course, he needed some information on need a bound for this function, what he calls psi of x, which is just d less than x lambda d. So this is his definition of psi of x. It's just the partial sums of the lambda d's. If I can, so he wants to know how to prove how this grows. Okay, so let me just say a few words about that and what he did in order to talk about this. So it's actually, you know, when you have a good idea and it works at least a little bit, and then you get stuck, it's probably worth the effort to push it forward a little bit because it was a good idea. So now we have here, we suspect that if the number of primes, or number of prime powers in general, is about x over log x, and we are weighting each prime by log of d, most likely this is like O of x, perhaps. Perhaps this is the case. Let us suppose so. For a moment. I'll come back to it in a second. And if that's the case, then it allows me to handle this error term. Then, summation d less than x, x lambda d over d, plus O of x equals this guy, x log x, plus, minus x plus O of log x. So we get an equality, okay? And now what would you like to do? We would like to divide the whole mess by x. So if I divide this by x, I get O of 1. This by x, I get log x. This by x, I get minus 1, but minus 1 is O of 1. You haven't told me what that thing is, so what's the point of carrying the minus 1 there, right? It's O of 1. And then divide by x, that's log x over x. But log x over x goes to 0, O of 1 is the larger error term, so you just put O of 1. Okay, so you end up getting this remarkable result. Okay, from that. So the only question is, what about this? Because I assumed this in order to get here. And let's see what Chebyshev, how he did that. Very clever idea. So Chebyshev, in the early days of this whole question, recognized that psi of x, which is d less than x lambda d, is an important function to study instead of the prime counting function. Pi of x is more natural than pi of x, which is the prime counting function. And I'm going to leave these as exercises now using Abel's lemma. Oh, one more thing before I do this. And he also defined theta of x, which is just the primes less than x, log p. Okay? So, what's the difference between theta of x and psi of x? Well, when p is a prime, this is going to spit out log p. So theta of x is in there. So clearly, theta of x is less than or equal to psi of x. All the primes are in there. But on the other hand, what's the difference between the two? Well, it's going to, this is also counting prime powers. So it's counting squares of primes, cubes of primes, and so on and so forth. And how many squares of primes are there up to x? At most root x. And what's the contribution of each of those things? At most root x log x. How many cubes are there at most? X to the 1/3. And what is it going to contribute? Log x. So it's x to the 1/3 log x. So you just keep on counting how many powers there could possibly be. And it isn't very difficult to show that psi of x and theta of x are pretty close to each other, and they only differ by something like that. Okay, so it's a small exercise for you to do. So psi of x and theta of x are very close together, and the error term is x to the half log x, because those are the prime powers, cubes, and so on and so forth, right? Okay, so you get that. So what Chebyshev proved was pi of x being asymptotic to x over log x is completely equivalent to theta of x being asymptotic to x, which is completely equivalent to psi of x being asymptotic to x. And these assertions are all exercises in Abel's lemma. You just have to see how we put it together. It's very straightforward. So exercises in Abel's lemma. So that same old lemma that he used. So if I want to prove this, it suffices to prove this, or it suffices to prove this. So this is what he was after, once he got that. Now let's go back and see how he actually proved this. Well, it's a very brilliant idea. He made the following observation. If I look at the binomial coefficient 2n choose n, this binomial coefficient, you can see that if I take the binomial expansion of 1 plus 1 to the power 2n, this is one of the terms in the expansion. Therefore, it's clear that this is less than 2 to the 2n. Okay, so you get this inequality. And what is so great about this particular middle binomial coefficient? Well, it is divisible by all the primes that lie between n and 2n. Because all the primes that lie between n and 2n appear in the numerator, but they're not cancelled by the thing in the denominator. Clever, huh? So this is the kind of observational skills that you must acquire if you want to call yourself a scientist or a mathematician, right? You have to kind of make these. Everybody just looks at these things and just says, "Yeah, it's interesting," and moves on. But the real scientist will say, "No, hold on. This, of course, it's obvious, but there's something interesting going on." To see something interesting going on in the obvious is what we have to cultivate. Okay? So here we have all the primes between n and 2n as divisors of this thing. And therefore, if I take log, so this number is less than this number. So I take logs, summation log p between n and 2n, okay, this strict inequality, is less than 2n log 2. Just take logs. Whatever this binomial coefficient is less than 2 to the 2n. This is a divisor of that binomial coefficient. Therefore, this number has to be less than this. Take logs and you get this. And in his notation with this theta thing, so this says theta 2n minus theta of n is less than 2n log 2. Iterate this one more time. Theta n minus theta n over 2 is less than n log 2. And then keep on going. Add them up, they cancel. It's a kind of telescoping sum. And so lo and behold, you'll get theta 2n is less than 4n log 2. In other words, he's managed to show that theta of x is O of x. Okay, theta of x is O of x. So using that, he says, well, psi of x and theta of x don't differ by very much. They differ by root x. Therefore, root x is much smaller than x. So if I got theta of x is O of x, so is psi of x O of x. Because x to the half is much smaller than x. Okay, so this is now done. Okay? Now, if you have this, you can see that this first half of the inequality comes through. So, having theta of x is O of x means this, right? For some, it's that. So, in other words, and I can split this up into p less than root x log p and p bigger than root x log p, and recognize that this guy is O of root x log x, and then this guy is now pi, summation log p root x p x is bounded by kx plus O of x to the half log x. And now here we have a lower bound. So each of these terms here is at least log of root x. So 1/2 log x times the number of primes from x, number of primes up to root x, is bounded by kx plus O of x to the half log x. Okay? And now keeping in mind that pi of root x is the number of primes up to root x, and that it's O of root x. It's a stupid estimate, but let's put it in anyway. You see that pi of x now is less than some other constant, b x over log x. I hope this is all clear. You can see the power of the O method. The big O symbol is very convenient, and you don't get bogged down by trying to keep track of constants when it's not necessary. Of course, sometimes it might be necessary, but in this case it's not. It's to your advantage. So essentially this is irrelevant. You get pi of x log x times a half is bounded by some kx. This is also smaller than this, therefore it's okay. So therefore pi of x is less than bx over log x. So he manages to prove the first estimate in this fashion, using only that little trick with the binomial coefficient. Okay? And then the other part is done using this. With the other part, for the lower bound, we have the following. So you have summation log p over p less than x. So from here, I want to go to only primes. There are prime powers also here, but the prime power contribution is very small compared to, in fact, the prime power contribution, by the way, is a convergent series. Because every time, see, when d is a prime, it's a log p over p. But d is a prime power, it's going to be p squared, p cubed, so on and so forth. But summation log p over p squared converges. Log p over p cubed converges. So all that stuff is a convergent series. So it isn't difficult to see that this from star, we have this equality, or asymptotic. And therefore, if what is this O of 1? It's a certain constant, isn't it? This thing. So if I choose some delta sufficiently small so that, or if you like, actually, this is the way you do it. Choose A sufficiently large. Choose A large so that if I take x over A so up to x it's log x plus O of 1, up to x over A it's log of x over A plus O of 1. Take the difference, plus O of 1, right? So what have I done? Keep in mind that this O of 1 is a fixed quantity here. I'm going to choose my A really gargantuan so that this is bigger than that thing. So that I can say it's bigger than some constant C0. So the sum here in between these two intervals is bigger than some C0 here. And then what do I say? I say that this is a decreasing sequence. The largest term is really at this lower end. So the smallest term, yeah, the larger term is at the other end. So now you can see that log of x over A divided by x over A times the number of primes between x minus x over A is bigger than some constant C0. And so from here you can see that pi of x minus pi of x over a is bigger than a constant x over a divided by log x over a. And therefore, since this is the lower bound for the number of primes up to x, you end up getting the lower bound there. Okay, so you end up getting the Chebyshev theorems by just using two ingredients. One is Abel's lemma, and the other is that binomial coefficient trick, but putting all of these things very cleverly together. Okay, so I think this is enough for the first day. Especially, I think it's quite a bit of stuff. Gives you an introduction of how to use the thing. So next time we meet, which is Friday, I guess, I will try to give you more details and how to use these techniques and understand more about prime numbers and other functions. Are there any questions or anything like that you would ask? Okay. If you have any questions, you can always ask them privately to me or bring them along for next time.